Good morning, everyone. I'm excited to share with you a concept that we believe will fundamentally change how humanoid robots learn to perform real-world tasks. Today's presentation is about imitation learning, and specifically, why sensor-embedded gloves are the key to making it practical, scalable, and fast. Let me start by framing the problem. There is a massive gap between what humans can do with their hands and what robots can replicate. Humans intuitively adjust grip strength, finger positioning, and applied pressure, all in real time, without conscious thought. Teaching a robot to do the same has traditionally required thousands of demonstrations, complex calibration, and extensive trial and error. Imitation learning offers a promising solution. Instead of programming every movement, the robot simply observes and copies what a human does. But the challenge has always been the quality of the data captured during those demonstrations. That is where sensor-embedded gloves come in. By equipping both the human demonstrator and the humanoid robot with identical sensor-embedded gloves, we create a shared data interface that captures pressure, force, position, and temperature, the four critical dimensions of tactile interaction. The result? Fast convergence. The humanoid can learn from the very first demonstration. No lengthy trial and error cycles, no complex recalibration between sessions. Over the next few slides, we will walk you through how this works, why identical gloves are essential, and how our approach dramatically outperforms traditional methods. Let us begin. We are here to introduce a breakthrough concept in humanoid robotics, imitation learning via shared disposable gloves. The central idea is elegantly simple. A human demonstrator and a humanoid robot wear the exact same pair of sensor-embedded disposable gloves. The human performs a household task, cooking, cleaning, organizing, and the humanoid watches and replicates those motions in real time. Our tagline captures it perfectly: one glove, two hands, infinite tasks. By using identical gloves as the shared interface, we eliminate the traditional calibration gap between human demonstration and robot execution. The human demonstrates, and the humanoid replicates, seamlessly, accurately, and immediately. Let me walk you through the three foundational pillars of this concept. First, the same gloves principle. Both human and humanoid wear identical disposable gloves embedded with the same sensor arrays. Second, home tasks. Our focus is on everyday household activities such as cooking, cleaning, and routine chores. And third, learn by watching. The humanoid mimics human motions captured through the glove sensors in real time. Now, let us examine why identical gloves are so critical to making this work. This slide addresses a fundamental question: why must the gloves be identical? The answer lies in the principle of data consistency. For imitation learning to achieve accurate motion replication, the sensor data streams from the human demonstrator and the humanoid learner must be identical in format, resolution, and calibration. As you can see in the diagram, the data flow is straightforward. The human hand, equipped with sensor-embedded gloves, generates tactile and kinematic data. That same sensor configuration is replicated on the humanoid hand. Because the sensor arrays are identical, we achieve one-to-one motion mapping without any calibration offset. This is the key insight that differentiates our approach. When both hands share identical sensor arrays, the humanoid receives the same tactile feedback data as the human demonstrator. There is no translation layer, no approximation, no signal loss. The gloves capture four critical data streams: pressure, force, position, and temperature. These four modalities provide a comprehensive tactile profile that enables the humanoid to not only replicate movements but also understand the physical context of each action: how firmly to grip, where to apply force, and how to respond to thermal feedback. Same sensors, same data, seamless transfer. That is the foundation upon which everything else is built. Now, let me show you why sensor-embedded gloves represent a significant leap over traditional approaches. Now, let us compare our approach with the traditional method of imitation learning, and you will see why sensor-embedded gloves represent a true paradigm shift. On the left side of this slide, you see the traditional approach. It relies solely on vision data. Cameras observe the human's hand motions from an external perspective. The system then attempts to reconstruct what the hand did through trial and error, because it cannot directly sense the forces being applied or the precise angles of each finger joint. This process is inherently slow. It requires many demonstrations, sometimes dozens or even hundreds, before the robot converges on an accurate reproduction of the task. On the right side, you see our approach. We still capture vision data. Camera-based tracking of finger movements and hand motion trajectories remains an important input. But here is the critical difference. We add a second, far richer data channel. The sensor-embedded gloves directly measure bend angles and applied pressure at every finger joint, in real time. The result is fast convergence. Instead of requiring dozens of demonstrations, the humanoid can learn from the very first demonstration. Vision data combined with direct sensor measurements eliminates the guesswork entirely. To put it simply, the traditional approach is slow because it infers. Our approach is fast because it measures. That is the fundamental advantage of sensor-embedded gloves in accelerating imitation learning. Think of it this way: imagine trying to learn to play piano by only watching someone's hands from across the room, versus having sensors on your fingers that tell you exactly how hard each key is pressed and at what angle each finger bends. The difference in learning speed would be enormous. That is exactly the advantage we are bringing to humanoid robotics. With this foundation in place, let me now walk you through the specific tasks we have validated with this technology.
Start at the top, draw the line down. Good. Now the crossbar. Excellent. Try the next one here. Now try to match my speed. Yes, exactly like that. Great job. That's perfect, exactly like that. Now let's try a shirt. Acknowledged. The efficiency rating for this method is optimal.
Okay, watch closely. We need to grip the sushi firmly but gently. The pressure sensors on the gloves help maintain the perfect hold. Now lift it smoothly